In the Chapter 1, Part 3 podcast, we're going to talk about how science helps us understand our world. So we'll be talking about how science depends on skepticism as well as reproducibility. We'll talk about inductive versus deductive reasoning, and we'll also touch on the scientific method.
Alright, this is technically an environmental science class. You're not getting out of here before we talk science. Science does help us understand our world. For definition's purposes, science is a process for producing knowledge based on observations. As scientists, we develop or test theories, which are proposed explanations of how a process works using these observations. Science can also refer to the cumulative body of knowledge produced by many scientists. We never rely on one person or one set of research. We tend to try to refute each other all the time. But science does rest on the assumption that the world is knowable and that we can learn about it by careful observation and logical reasoning. There's a list of basic principles of science in your textbook. It's table 1.2, and I just wanted to highlight a couple ideas from this table. The first is uniformitarianism. This is that you have these basic patterns and processes that are uniform across time and space, and the forces that were at work a long time ago that shaped our Earth in the past are the same ones that are still at work today. So there wasn't something different going on a million years ago than there is today. It's uniform across space and time. There's also a certain amount of uncertainty in science. Knowledge does change as new evidence appears, and explanations change with new evidence, and theories based on current evidence have to be tested on additional evidence with the understanding that new data may disprove even the best theories. So there's the only element that is consistent in science is change as we discover new ideas. Also, tests have to be repeatable. I can't just tell you that something happened in my lab. Somebody else has to be able to reproduce that. Another important idea is proof is elusive. A lot of times the layperson will say, well, prove it. How do you know for sure? What's your proof? And we don't tend to like to use the word proof in science because we rarely expect science to provide absolute proof that a theory is correct, because we know that theories and ideas and it changes over time, and it changes with the addition of new evidence. So that's something that we tend to want to avoid. To be a good scientist, you gotta be skeptical, and science also depends on reproducibility. So ideally, scientists are considered skeptics. They are cautious about accepting proposed explanations until you have a good body of evidence to support it. Not just one study, but multiple repeated studies and different people working on a particular problem. And it also has to be reproducible. If someone else can't reproduce your work, there's a lot of question about whether you drew the right conclusions in the first place, or that your outcome wasn't a fluke. Alright, let's talk about the difference between deductive and inductive reasoning. Ideally, scientists are going to deduce conclusions from general laws that they know to be true. So first, let's talk about deductive reasoning. That's logical reasoning from general to specific. So for example, if I know that massive objects attract each other, so force of gravity, I know that's my general idea. I know then if I drop an apple, it's going to fall towards the earth, towards a massive object. That's more specific. That is an example of deductive reasoning. Now, conversely, you can reason from many observations to produce a general rule, and that would be called inductive reasoning. So if I notice that throughout the course of a year, birds tend to appear and disappear, and that is true all over the world, that's my specific observation, and I've taken a lot of observations, I could then induce that birds are migratory and that they spend certain times or amounts of time in different places around the world. That's an example of inductive reasoning. When we talk about the scientific method, we're talking about an orderly way to examine problems. So generally speaking, we take the same approach to every problem or question that we have. So the first step is to make an observation and identify a question. Most likely as a scientist, if you ask yourself a question, the next step is going to be to research that question. It could be that a quick Google search shows that the question you had has already been answered. It was general knowledge. You would want to look up as much as you can about that particular question to see if there is even a need for investigation. If there is, you can then propose a hypothesis, and this is an expected outcome to the question or the problem at hand. It is not an educated guess. You are not guessing at this point. You've researched it, you know a lot about the subject. Then you get to test your hypothesis, and that's the fun part. That's doing the science. You'll gather data from your test, and then looking at your data, looking at your errors, you'll be able to interpret your results and draw a conclusion from that. This is a table or an image from your book, and so they go through identifying a question, forming a testable hypothesis, developing a test for the hypothesis. You'll collect your data from your test and you'll interpret your results. At this point, they show that, hey, we may have to go back and refine and revise our original hypothesis and then test again. It could be that you found the way you tested was not a good indicator of what you were trying to find, or whatever the case may be. Once you're pretty happy with the results you get and you're pretty sure that that answers your hypothesis, then our last step is to report for peer review, or to get your paper published or your research published in a journal that matches whatever scientific discipline that you're in. All right, if you understand probability, that does reduce uncertainty. So probability is the measure of how likely something is to occur. It is incredibly likely that the sun is going to come up tomorrow, just like it did for the last billion years. Probability, however, does not tell you what will happen. So we don't know for sure the sun's going to come up tomorrow. Something could happen. But it tells you what's likely to happen. We're pretty sure the sun's going to come up tomorrow. Science is a cumulative process. We have this idea of consensus, which is very important in science. It's where a community of scientists collaborates in a cumulative self-correcting process. So oftentimes we have problems that are being worked on by scientists, and each scientist is contributing a portion of our understanding of that particular problem. And it's that collaboration that can be cumulative. So we're gaining insights from all our different scientists working on the problem from different angles, and it can be very self-correcting. Oftentimes we have new ideas that emerge, and these can cause major shifts in scientific consensus. Thomas Kuhn described this idea called a paradigm shift. And according to him, paradigm shifts occur when a majority of scientists accept that the old explanation no longer describes the new observations very well. And so what you wind up with are these major shifts in scientific consensus, and they're great changes in explanatory frameworks. An example your book uses is about 2 centuries ago, many geologists accepted that the features on the face of the earth, the valleys where the boulders are placed, were a result of a flood. One particular scientist said, when these were placed here, there was an ice age, we had glaciers. That accounts better for the movement of those boulders as well as for these geologic features. So that represented a paradigm shift amongst geologists when that information came out. All right, a couple of things you need to be thinking about as you're listening to scientific reports or you're listening to the media talk about science is, what is sound science? When controversies surround science, we see claims about sound science and accusations of junk science arising. What does it mean? Who do you know who's right? When you hear arguments about whose science is valid, you do have to remember the basic principles of science. Are these disputed studies reproducible? Are conclusions drawn with caution, skepticism? Are the samples large? Are they random? Are conclusions supported by a majority of scholars who have studied the problem? Do any of the experts have an economic interest in the outcome? And that one's especially important for us. So table 1.3 in your book gives us a bunch of questions that you want to ask yourself anytime you're trying to evaluate new science that comes out or scientific claims that come out. Oftentimes in science, we ask ourselves, how do I know that what you just said is true? And part of the way that we evaluate arguments in science has to do with observable evidence or data. It also has to do with logical reasoning from evidence. So we use critical thinking, which is an ability to think critically, clearly, and analytically about a problem. It may be the most valuable skill that you take away from this class, I hope. So here's a list of some questions that you would ask yourself in critical thinking. What is the purpose of my thinking? What precise question am I trying to answer? Within what point of view am I thinking? What information am I using? How am I interpreting that information? What concepts are central to my thinking? What conclusions am I aiming towards? What am I taking for granted? Are there assumptions that I'm making? If I accept the conclusions, what are some of those implications? And what would be the consequence if I put my thoughts into action? So critical thinking takes a long time to develop, but these are some questions that kind of get you started when you're thinking about a specific problem. Something to keep in mind is that critical thinking processes are self-reflective as well as self-correcting. A lot of times they're going to help you discover hidden meanings in claims and evaluate arguments, recognize differences between facts and values, and help you to avoid jumping to any conclusions. There's different aspects of critical thinking to keep in mind. Analytical thinking can help you break down a problem into its constituent parts. Creative thinking asks, how might I approach this problem in a new and inventive way? Logical thinking will evaluate whether the structure of your argument makes sense. And reflective thinking asks, what does it all mean? So putting all of these questions together helps you to become a better critical thinker and allows you to carefully examine what you are trying to accomplish and how you'll know when you have the answer. And finally, our big takeaway is that critical thinking can help you to learn environmental science. Anytime you're reading your textbook or you hear the news or you're watching TV, try to distinguish between statements of fact and statements of opinion. I know a lot of media sources try to be unbiased, but there is a lot of bias within us as well. Most of us try to be fair and even-handed in presenting controversies, but our personal biases and values, some of which we may not even recognize, can affect how we see issues and how we present arguments. So watch for cases in which you need to think for yourself and use critical and reflective thinking skills to uncover the truth. And remember that critical thinking evaluates premises, contradictions, as well as assumptions.